Yeah, okay, let's try that. So just to continue from last lecture on Tuesday, we ended with a four-dimensional gauge supergravity. I wrote the action and supersymmetry variations, etc. And then I gave a few examples of supersymmetric solutions that solve the Killing spinor equations. And we really ended with an example of a supersymmetric black hole. Perhaps I should have added that these are very interesting objects to study. They are peculiar because they carry an entropy, but they have zero temperature. So it's kind of interesting to study these examples. So there are some physical motivation for that. The other thing which I mentioned about four-dimensional supergravity is that it is directly related to 11-dimensional supergravity, which is what I'm going to talk about now. Okay, so this can be embedded or uplifted to D equal 11 supergravity. So the reason why I can talk about D equal 11 supergravity without specifying which version is that in 11 dimension it is unique. So it's the unique supergravity that one can write in 11 dimension. And 11 dimensions is also the maximum number of dimensions in which one can formulate a theory of supergravity just with a metric, so only one graviton. So let's write the field content. We have the good old field bane or metric, and then we definitely have the good old gravitino. But in addition, as I mentioned on Tuesday, in order to write the action of shell, so that it is supersymmetric of shell, one needs to introduce an additional field, which in this case is a three-form field. I will use the notation C mu rho. So it's a three-form or antisymmetric field. With field strength, which often is called G, is a four-form. So sometimes this G in the supergravity literature is also called flux. G flux. Okay. Also here we are in definite dimensions, so I can specify many properties of gamma matrices and spinors and so on. The thing worth mentioning is that this is assumed to be a Majorana spinor, so the minimal representations. Right. So there is a reality condition that one can impose in 11 dimensions. The action is very simple, so it has several interesting properties. It is unique, and it is also arguably one of the simplest supergravity that one can write. And as I will explain later, essentially all the supergravities follow can be derived from 11-dimensional supergravity in a sense that I will explain. So there is some Newton constant. And there is a kinetic term for the fourth form. Let me abbreviate it G square, just the contraction of the four indices. And then a new kind of object in our context, in our lectures, is this interaction here, which is written in terms of, so here everything is inside these brackets. So this is a term which can exist only in the odd dimensions, and it's it's somehow a funny object, is a kind of Chern-Simons term. And it involves the field strength as well as the potential itself. So this is a fourth form, and so together it forms a volume form in 11 dimensions. So that's somehow analogous to what you may have seen in D equal 3. You can write something like A wedge F, right? That's normally called the Chern-Simons term in 3 dimensions. There are, of course, fermions, namely terms that involve the gravitino. But from here on, I will not write them anymore. So I stopped writing them in the equations of motion at the end of the last lecture. And from now on, I will also stop writing the fermionic terms in the action. We know that they are there. They must be there for the action to be supersymmetric. And somehow, the only remnant of the fermionic part of the supergravity theories, it's always the supersymmetry variations. And in particular, if you're interested in finding solution to the Killing-Spinor equations, then we have to specify the variation of the gravitino and of the other fermions if there are additional fermions. So in this case, the variation of the gravitino that yields the Killing-Spinor equation is the following. Let me write it. So first of all, I will write it in this universal form, right? So as promised, I can always write this in this form. And then I have to specify what's my d hat. And we already starting from the simplest case, where it's just the ordinary covariant derivative with the spin connection. We added the cosmological term. Then we added the gauge term in 4 dimensions. And here there is a term that depends on the field here, on the bosonic part of the field, and in terms of some gamma matrices. So let's write this. So there is some combinatorial factor, 1/288, gamma mu sigma minus 8. Okay. So in some conventions, which are quite common, and the important thing about convention is that the convention on the supersymmetry variations are compatible with the conventions that one is using in the action, of course. In this case, this depends on a term with 5 gamma matrices antisymmetrized and 3 gamma matrices antisymmetrized with appropriate contractions. Okay. The equations of motion, similarly to the one in 4 dimensions that we discussed, have the Einstein equation. And actually, I will not write explicitly the energy momentum tensor that you compute from G. It's some expression. And then let's write the corresponding Maxwell equation, which contains this extra term arising from the Chern-Simons term. So I refer to this as Maxwell equation, although it clearly is not the original Maxwell equation, because it takes the same form apart from this shift when you're writing in terms of a Hodge star and differential form. But in this case, you have to remember this is a 4th form, and this becomes a 7th form, so this is an 8th form, and that's why you have to sum this 8th form here. So the study of supersymmetric solutions of 11-dimensional supergravity is of great interest. It has been, there are many interesting solutions that have been found many years ago, and then when about 20 years ago people started to explore systematically with these techniques which I mentioned last time, then various classifications of the supersymmetric solutions started to be written down. And also of particular interest for these lectures is the fact that there are many solutions which contain an anti-de Sitter factor. So you have solutions which have ADS4, ADS5, ADS3, in fact, many possible cases. So before mentioning some interesting example, let me say another reason why 11-dimensional supergravity is important. And the reason is that this is sometimes referred as the low energy of M theory. Okay. So as 10-dimensional supergravity is, in some sense, the low energy limit of superstring theory, type 2A, type 2B, and all the various versions. In the same sense, 11-dimensional supergravity is believed to be the low energy limit of some bigger theory, some quantum theory, which should encompass all the string theories and extend that, which has been dubbed M theory, although we really don't know exactly what this theory is. But that has not prevented people to refer to M theory for many, many years. And in many contexts, and one can often refer to 11-dimensional supergravity as M theory itself. Right? So that's sometimes one refers to 11-dimensional supergravity saying M theory. But the M theory, strictly speaking, should be a bigger theory. Now, the way in which 11-dimensional supergravity contains the other supergravities is by reduction, so compactification to lower dimensions. So let me sketch a small table where we have some relationships between different theories. So on this side, I will write the 11-dimensional supergravity, and by the process of Kaluza-Klein reduction, or just simply dimensional reduction, going from d equal 11 to d equal 10, one obtains type 2A supergravity. And then here, let me put an arrow. So here, this is supposed to be the low energy limit, so low energy. And here we have a type 2A string theory. Now, there are various dualities, as you may have heard in the context of string theory, or maybe not yet, but you will hear. And one particular duality which arises in string theory is called T-Duality. And there is also a supergravity version of this duality that exchange type 2A and type 2B. Okay, so type 2A is related to type 2B by T-duality, and there is the same duality that you can implement directly at the level of the string worksheet. In this context, they are called Buscher's T-duality, or some generalization thereof. So this part we know, and you will probably hear something in the string theory lectures about how the low energy limit of the massless modes of string theory actually rearranges itself into exactly this type 2A and type 2B supergravity actions. And finally, so all of these things are known, and they are fact, they are proved. But then there are another two arrows which would complete this diagram, this schematic diagram. So here we put M theory, and I will make a dashed arrow. Okay, so this is supposed to be conjectured. So the low energy limit of M theory should give 11-dimensional supergravity, and on the other side, the reduction from M theory directly to 10 dimension should give string theory. Okay, so this is also conjecture. Okay, you can start adding more arrows by doing more dualities and including type 1, heterotic, and so on. But this is how I wanted to kind of present and motivate M theory. So in most practical applications that we will consider, we can work at the level of 11-dimensional supergravity, taking into account some quantum effect, which, for example, boils down to some particular quantization condition on the fluxes that have to be obeyed, which are the so-called Dirac quantization conditions. So let me mention briefly, although I will not go into the details of these, but on the type 2B counterpart, two well-known solutions that were found long time ago, about 30 years ago, or even more perhaps. And these are, in a simple notation, direct product of anti-de Sitter 4 times a 7-dimensional sphere and anti-de Sitter 7 times 4-dimensional sphere. So this takes into account the form of the metric. The metric is just a sum, direct sum of the metric on anti-de Sitter and a metric on the sphere. And you have to specify, to complete a solution, what is the form of the G flux. And the G flux here is proportional, so it's very symmetric. It's proportional to the volume form of ADS4. Okay, so this notation indicates a 4 form. And similarly here, G is proportional to the volume form of S4. In fact, both solutions preserve maximal amount of supersymmetry, which is 32, so fraction 1. 32 is the dimension of the spinor, so of the spinorial part of the gravitino, or of the supersymmetry parameter epsilon. So that means that there are 32 independent solutions to that equation there over the reals, right? So because we are taking Majorana condition. In fact, all the maximally supersymmetric solutions are classified, and there are not many, but these are the two examples that are very relevant, obviously, for ADS CFT. So if we had more time and more lectures, at some point I would be talking about the field theory dual, the conformal field theory dual of these ADS4 and ADS7 solutions, but we don't have that time. So I will concentrate, starting from the end of the lecture today and starting better on Monday, next week when we have the lecture. I think on Monday we'll discuss the analogous case that arises in type 2B, right? So I will discuss the famous ADS5 cross S5 in gory detail. But I wanted to mention that in M theory, these are the counterpart of that. So let's raise that. So notice the important fact that as soon as we have to deal with 11 dimensions or 10 dimensions, and we want some anti-de Sitter factor, then we need to complement the solution with some internal part. And these are simple ways to complement the solution, so with spheres. So we have S7, S4, and as I mentioned, there will be the solution ADS5 cross S5. So the internal part plays a role as well as the anti-de Sitter factor. So there is some physics in the sense of the ADS-CFT correspondence, both in anti-de Sitter as well as in the internal part. So that will play a crucial role. So next thing I would like to talk about, starting from taking from M theory, type 2A and type 2B. Although our main example will be a solution of type 2B supergravity, because I'm starting here from 11 dimensions, and then I'm taking this route. The first step, the simplest step, the reduction to get type 2A supergravity, and then if you wanted, we'll not actually do the details, but one could do the T-Duality and obtain to be supergravity. So, yeah. It's unique in 11 dimensions. Yes. So by solution, we normally mean a configuration of bosonic fields that solve the equations of motion, right? So normally, if I want to say that it preserves supersymmetry, I say a supersymmetric solution. But sometimes I might forget to mention supersymmetric. But in any case, normally a solution is a configuration that solves the equation of motion. And you also need, if you want supersymmetry, you have to impose supersymmetry. Importantly, you have to remember that although there is a folklore theorem or folklore understanding that supersymmetry implies the equations of motion, it is not completely true. It only implies part of them. So you should always, in the end, impose the equations of motion, because supersymmetry does not impose all the equations of motion in general. So you might have heard that this is true. Okay. So in Rodolfo's lectures, maybe at some point you will derive the spectrum of type 2A and type 2B from string theory, hopefully. And it's possible, although I'm not sure that he will have time to discuss, to show that from the interactions, really, of the, like if you write the vertex operators and so on in string theory, you can derive the term that you can then repackage into the actions for type 2A and type 2B. And so the actions, because they are supergravity actions, will always start with the Ricci scalar, and then we'll have all the other terms that contain the interactions with the other fields, right? So obviously I will not do that, but I will do a small exercise, a short exercise of deriving the spectrum of type 2A from reducing from the 11-dimensional supergravity down to 10-dimensional type 2A. So let's focus now on on type 2A. And okay, so what do we have? So here we start from d equal 11, and we do our reduction. So the reduction to d equal 10 means in practice the following. So you take your gravitino, and then you can specify the index mu that normally takes values between 0 and 10 to some index which I will conventionally call it 11, and another index that will take values I between 0 and 9. Right? So you split the indices, you do this split of the Lorentz group in 11 dimensions, and you get the following fields. You get some psi I, and in fact, if you trace the properties of the decomposition of the spinors and the gamma matrices and so on, you get from one spinor in 11 dimensions, you get two spinors of opposite chiralities in 10 dimensions. So I will put a plus and a minus. They both come from the same big spinor there. Yeah, if you count the dimension, you will see that they match. And then you get, if you fix mu to be 11, you get, again, two chiralities So they have no indices now in 10 dimensions. And these are called Majorana Weil. These are Majorana Weil. And they are called dilatinos. Okay? Whereas these are two Majorana Weil gravitinos. So this is as far as the fermions are concerned. So now we see that in fact in 10 dimensions there isn't only a gravitino. Actually there are two gravitinos, and that's why the reason they're called type 2 theories actually. But there are also additional fermions which arise from this 11-dimensional component of the gravitino up in 11 dimensions. And these are the dilatinos. There are no other fermions, so we're done with that. Let's look at the bosonic fields. The bosonic fields arise from the metric and from the C field. So from the C field, let's see if we can fit. No, maybe we will not fit here. So let's use this for the C field. We have to do a similar exercise in decomposing the Lorentz structure. We have to remember that these are totally anti-symmetrized. Okay, so I can never have two indices the same. So we have here Cij, and then we have C11ij, right? And I can't have two indices that are simultaneously 11, so that's all I have. So this I will rename A with the upper script 3, ijk, and this is now a two-form, so an antisymmetric field in two indices, which I will rename Bij, okay? Now, okay, my table will not fit as in my page, but nevertheless I will use the other board. So this is a Ramon-Ramon field in the language of string theory, whereas this is a Schwarz field, and it is known often as B field. Also in the old days was called Kalb-Ramon field, I think. And finally, let's consider the metric. It will give us a few more fields. Clearly, it will give us a metric in 10D. And what else does it give us? Let's see. So from the metric in 11 dimensions, we get three types of fields. We get a metric Gij. We get a Lorentz vector in 10 dimensions. Well, let's first write the Lorentz scalar from the 11 component of the metric, and then we get a Lorentz vector 11i. Okay, so this I will just keep the name Gij. The scalar I will define it as e to the phi, and the vector I will call it a upper script I. Okay, so this is another Ramon-Ramon field. This is Neveu-Schwarz dilaton, and this is just the metric. Okay, so if you have seen it, good. If you have not seen it, I have anticipated what you will see. That comprises the entire spectrum of type 2a supergravity, which is the massless sector of type 2a string theory. Okay. One interesting fact that will play a role in our ADS-CFT story is that these fields, as the electric field couples to electron and charged particles, they couple to certain objects which have charge under the Ramon-Ramon fields, as well as also under the Neveu-Schwarz one. And these are the famous branes, right? So these are extended objects. So let's write them here, maybe with a different color. So the one from here is the most similar to the one to the electron, right? So this is like the Maxwell field. and this coupled to a particle, which is called the zero brane. It also couples, in a way that I'm just going to explain in a second, to an extended object in 10 dimensions, which is called the 6 brane. All the Neveu-Schwarz fields, so I should put them all together somehow. So allow me this little dirty trick to join two blackboards. So all the Neveu-Schwarz fields couple to the fundamental string, which is referred to as F1, and the Neveu-Schwarz 5 brane. And finally, the Ramon-Ramon triform couples to an object which is called the 2 brane, the 2 brane, as well as the magnetic dual D4. Okay, so why do they couple to two kind of objects? We don't really observe this normally in 4 dimensions. So there is the electron, and there isn't anything else. But there is the monopole, if you really think about electromagnetic duality. In that case, it has the same dimension. But here, because we are in the potential have different dimensionalities, and we are in fixed 10 dimensions, then the magnetic duality arises as follows. So if you take any C potential, let's say Cp plus 1, where Cp plus 1 can be A1 or say A3 or B, okay? This commas means or. Then you can define a dual potential by taking star dc p plus 1 and just defining this to be d of a dual potential C tilde. The fact that you can do that arises from the Maxwell equation for these potentials, right? So locally you can always introduce such potential. And if you want this to be p plus 1 tilde, then you find that short exercise in counting dimensions, p tilde is equal to 6 minus p. Right? And this 6 has to do with the dimension of space-time being 10. In different dimension, you would have a different factor for the magnetic dual. So these are the magnetic dual potentials, and as the lower dimensional object couple to the original potentials, the higher dimensional ones couple to the magnetic potentials. Okay, so this is a 0-dimensional object. This is a 6-dimensional object. So it means that it has a 6 spatial plus 1 temporal direction, and so on. Right? And perhaps the one that you have heard already about is the string, of course, which is extended in 1 spatial dimension and has a 2-dimensional world sheet. And that you will see soon, I think, that it couples to the dilaton. You have probably seen the dilaton already in the context of the bosonic string, but there is also a version in the context of superstring. Okay, so I've done this seemingly a little bit in a sketchy way. So you would ask me, well, okay, but you have done these arrows and so on, but how about deriving the action? Actually, if we had a bit more time, we could completely derive the action, starting from this action here, just by putting all the factors and all the correct numbers in the relation between these fields in 11 dimensions to the fields in 10 dimensions. So this is a proper derivation. It can be promoted to a proper derivation of a 10-dimensional type 2A supergravity. And what I would like to, I've already mentioned, I would like to stress the existence of this extended object. So you have seen, or you will see soon, that this extended object, similarly to the string, they have some kind of a worldsheet description, and the D brane will be introduced as hyperplanes, as submanifolds in space-time, where the open string can attach. So in the context of supergravity, type 2A and type 2B, these D-branes will arise, I will explain that later, as solutions to the equations of motion, and they will be characterized by the presence of the various potentials, right? So, for example, there would be a D2 brane solution where all the fields are set to 0, apart from the Ramon-Ramon three-form flux and the metric and the dilaton. Right? So the metric and the dilaton actually always have to be switched on generically. So, for example, if we want to study the D2 brane solution, we will have, as I just said, 8, 3, G, I, J. Well, let's not put indices here. Well, let's put it 3K. And e to the phi only with all the other fields set to 0. And this fact, the fact that these objects, these branes, have two different descriptions, one in terms of strings and one in terms of solution to the supergravity equations, is at the heart of the IDS-CFT correspondence. Right? So I'm really mentioning that because it plays an important role in our story. So let me now briefly summarize. Well, actually, I will delete this because it was just meant to be an example. So let me now summarize more briefly the type 2B spectrum. So you could obtain that in various ways. You could obtain by doing a T-duality from the type 2A spectrum, or by quantizing the type 2B superstring that you might do probably later. So let me just quote it. It has a Neveu-Schwarz sector, which is exactly the same. So the Neveu-Schwarz sector is a universal. And it has a Ramon sector, which is complementary to the fields which appear in type 2A. So here the potentials are with an odd number of indices, whereas in type 2B they will have an even number of indices. So we have A0, we have A2, and we have A4. Okay, so in terms of extended object branes, we still have the fundamental string, obviously, as expected, and then the Neveu-Schwarz 5 brane, which is the magnetic dual. And then the correspondent object here are D branes, which are charged under the Ramon-Ramon fields. And as we have learned here from this part, the rule is that simply the way in the couple, the extended object has a one dimension extra. So this will couple to the D1 brane, and this will couple to the, D-1 brane. This will couple to the D1 brane, and this will couple to the D3 brane. Right? So the word volume of the D3 brane has 4 dimensions, and that's why it couples to a 4-dimensional potential, similarly to how the electron, which has a one-dimensional word volume, couples to the gauge field here. The magnetic dual of these D branes are the D7, the D5, and if you do the algebra there, well, actually I've done it for you, you will find that the magnetic dual of the D3 brane is still the D3 brane. Okay? So the D3 brane is, you can see already from here, it's a very special object among all the branes. And this fact goes together with the caveat, namely that the field strength of this A4, which is F5, has to be self-dual. The sign here depends on the convention that you have, right? But has to be self-dual. And the caveat is that actually, if you impose this condition, then F square is 0. So the action of type 2B supergravity cannot have an F squared term, because you have to impose this condition here to account correctly for the number of degrees of freedom. So the way out, the cheap way out, which nevertheless is commonly used, is to write the action with F squared, derive the equation of motion, find the corresponding energy momentum tensor, etc., and then at the end of the day impose the self-duality condition by hand. Yeah? Sorry, say it again. S dual, what? Is there an action including an imaginary field which has the self-duality condition? Oh, you mean if you can write an action where which contains somehow the kinetic term? Yes, yes, there is. It has some drawbacks. I think you have to introduce additional auxiliary fields, and somehow you have to break Lorentz invariants. I haven't seen this recently, so I wouldn't be able to write it down. But it was worked out by people, and it's a technique that actually you can use in other situations in different dimensions where you have to have fields which are self-dual, and you can't write an action for them, but then you can write. There is some procedure that allows you to write this action. Now, this procedure is not terribly popular because, of course, it solves the problem of writing an action, but it is not particularly simple or clean, I would say. So if you are interested in the end in the equations of motion and in finding solution to the equation of motion, then there is no advantage in starting with a more complicated and manifestly Lorentz, manifestly containing the field and the self-duality imposed. So it is possible, but it is not very common to work with that. Okay, so the next thing I want to do is to explain in more detail what are these solutions which I'm referring about that have these branes. And our focus will be on the D3 brane, but in fact the exercise of writing the solutions can be done in general. So I will do this in general for any D brane. Is there any question for now? Oh, sorry, today this is really bothering me. The organizers should find a better way to implement these microphones. Any questions? So if we're interested in the simple situation in which there is a solution that describes a 1D brane with a very humble flat word volume, nothing particularly advanced, I mean, you can then later start combining branes, intersecting them, wrapping them around manifolds, and it becomes very complicated and interesting. But if we start from the simplest situation in which one imagines your brain as an object like that, extended just in flat space-time, then you can write the action, a universal action. So let's say an effective description, which is obtained either from type 2A or type 2B. Okay, by setting to 0 all of the fields except those which are strictly necessary for the solution of describing the brane. So here we have a Newton constant, which in fact in 10 dimensions is inherited from the string. So I will start putting factor of ls, the string length related to the alpha prime, which you may have seen. And then, actually, can you hear me, or is it working this or not? Because I hear something, some noise. I'm not sure. It has to do with the microphone. So the action that one derives from string is naturally of this type, where it has a coupling of the dilaton with the metric that appears here in front of the Ricci scalar. And so this is the Neveu-Schwarz part, and the Ramon-Ramon part is contained into the field strength kinetic term for the various Ramon-Ramon fields, which with the factors is the following. Okay? So F is in general F p plus 2 is d a p plus 1. Okay? And here the rule is that you take a particular p. For example, if you're interested in the D2 brane, then we would pick here p equal whatever 2, and that would be the action for the D2 brane. So the fact that there is this dilaton factor means that the action is derived in a particular frame. Yes. Oh, good. Yes, thanks. It closes here. Yes. Yeah, it's an important thing because, as I was about to mention, this is the so-called string frame, ST. And then you could rewrite the action for a metric in so-called Einstein frame. So let me mention that. So the metric in Einstein frame, and here frame has a particular meaning. It's just a conformal factor in front of the metric. It's given by e to the minus phi over 2 g mu nu in the string frame. SF should say SF. Sorry, SF. Einstein frame. Okay. So the metric here, if you multiply by this conformal factor and you plug this in, you will get a different action, slightly different, where you have eliminated this and you have put it in the canonical form of the Einstein-Hilbert action, where it starts with just R, but then this will propagate and will, for example, reappear here with some power. So I'll mention that in a second. LS is also related to alpha prime. It's just a different notation, basically. Okay, so these are remnant of string theory that we will carry around. Right, so this is alpha prime, which appears here. And you might ask, how about coupling constants? Well, if you remember from your string theory, in string theory there are no coupling constant, which is one of the virtues of string theory. And the coupling constant arises as an expectation value of the dilaton. So G string is defined as the expectation value of e to the phi. Right? So sometimes we introduce explicitly GS in the action, and by that we mean the constant part of e to the phi. So in fact, it is useful to rewrite the action in Einstein frame. So let's do that. As the same 2 pi to the 7th ls square. Sorry, ls to the 8th. And then it has a more familiar looking term. So here I will put an E to remember that we are in Einstein frame. And now I don't have an extra parenthesis to worry about. This is the Ricci scalar of the metric in the Einstein frame. And this acquires a factor. And also this is a minus. By the way, you can find this in various references, but let me still write the factors. So there is some e to the some AP phi f squared p plus 2. Okay. Where AP is a constant that depends on p and is given by p minus 3 divided by 2. So the factors of 2 are not terribly important, but this p minus 3 term is interesting. It shows that for p equal 3, that corresponds to the D3 brane, that there is no coupling of the dilaton with the Ramon-Ramon field, and that will propagate in a special feature of the D3 brane solution that will just emerge after specifying p equal 3 in the general solution that I'm going to derive. Well, okay, so you could write an ansatz, plug into the equations of motion, and then try to derive it. It's an, yes?
If this can come from a length gravity from a reduction, why don't we see any dependence on the radius?
Because I've written this in terms of LS. Okay, so in this presentation, I imagine having derived that from doing scattering amplitude of strings, which I've never done for this, but anyway. What do you mean by R, sorry? Yeah.
Surely it's going to depend on what that radius is.
The radius is the dilaton. Sorry. Yeah. But sorry, I thought that you were worried about another point, which I was going to explain, and it's the relation to L Planck that you write the supergravity in 11 dimensions in terms of that. So if you do that, so there is a Newton constant in 11 dimensions basically that you write, and then that if you write this from 11 to 10, there is a relation between the 11-dimensional Newton constant and the 10-dimensional one, which is summarized by this relation here. Right. I also put GS by. So in other words, your question is more accurately answered by the fact that there is a GS factor. It's the constant part of the dilaton. Okay. So that's the relation between 11 and 10. But I will from now on work in conventions where we have either LS appearing explicitly or alpha prime, which is just equivalent. Okay, so I leave to you to derive the equations of motion for this action and then plug in ansatz. It's standard, interesting educational exercise. And I also give you the ansatz that you have to plug in so that that makes your life slightly easier. And the ansatz take this form. So I will explain what it means that this is an ansatz. And then I have to go in the second line. Yes. This is a 9. Okay, so let's describe this. So this is time, These are the spatial coordinates along the object that we want to describe. This is in the Einstein frame, yes. Well, the ansatz actually you can write in any frame, but then when I write the solution for H, they will be in the Einstein frame. So the coordinates on here are xi, and the coordinates transverse to the brain are called yi. And there are p+1 coordinates on this direction, and the remaining one, 9 minus p in the transverse direction. So that's the picture. R is defined as the distance, the transverse distance from the brain. So it is the sum of y coordinate squared plus y squared 9 minus p. Okay, so all of these things, they're not just coming, they're not derived from anything in particular. There are assumptions, right? So I'm assuming that the object has these symmetries, right? So I want something that has the symmetries of the Lorentz group on the space-time and also of the Lorentz group in the transverse space. And moreover, so that implies that this function here can be at best just a function of the radial distance. So in a sense, this is all kind of spherical. So with this assumption, and that's why I have these ansatz, if I plug this into the equations of motion, then I will reduce this to equations for H. In fact, I can also write the ansatz for the potential. So AP plus 1. And here I write this in these explicit components. Right? There is only one term. And it's minus 1/2 p r to the minus 1. So you could take this, plug into the equations, and that will give an equation for H that you can solve. And the solution is the following. So solution. So the subscript p means that it depends on p. And this is equal to 1 plus L to the 7 minus p divided by R to the 7 minus p. So this is a constant that is normalized to 1, just arbitrarily. And it has to do with the fact that for R going to infinity, so when you are far away from the brain, then this function reduces to 1, and then you recover on the nose the Minkowski metric. So far away from your object, you are just in flat, empty space. It's a trivial constant anyway, and it's conventionally put to 1. This other constant instead appears and is given in terms of this other factor, and I'm going to fix it in a second. I also wanted to write the dilaton, which I forgot previously. So e to the phi is also given in terms of this function h. And if I put an explicit constant part, the rest is a power of h, namely 3 minus p divided by 4. Okay, so now you have all the fields, right? So all the fields that enter the action, they have a profile, which is all given in terms of this function h. Okay, I told you the reason for the constant 1. So let me tell you how this other constant is fixed. By the way, you would recognize that this power that appears is the power corresponding to the fact that the function is harmonic in the transverse space. So it simply obeys the flat Laplacian in the transverse y coordinates. And that follows from the equations of motion, and it gives that power. Of course, you have to be very careful for p equals 7, 8, and so on. So let's say that we stay p low enough, because as this becomes 0, the D7 brane behave differently. You get actually some logarithmic term, and that has to do with the fact that you have a transverse Laplacian in 2 dimensions. So let's say for D3 brane and D2, D4, up to D5, we are safe. Now, the constant L is a constant, so it would be somehow just a modulus of your solution. In principle, it can take any value that you wish. However, you have to impose this quantization condition, which I mentioned. And the quantization condition is that if you take a cycle that surrounds at infinity your brane, your object, so it has a sphere at infinity, which is an 8 minus p dimensional sphere, and you integrate star f over this, then up to some factors which are the following, this has to be an integer. Okay, so I will call this n, an integer, positive integer. And this n, it's naturally interpreted as the number of branes. Let's say p branes. I say p branes because this is also valid for the Neveu-Schwarz brane, for example, as well as for the d branes. Right? So because you have to impose this condition, and where here is n is an arbitrary number at this stage, an arbitrary integer number, then you plug it in, and then, well, there is only one free constant, and this free constant is fixed by this condition. So the free constant turns out to be the following. Two pi let me not give a dp. It's not very important. You can read off. These are factors of 2 and pi. So other factors, let's say. You can find that anyway in the literature. So it will be important for us to trace the dependence on ls, on gs, and of n. Yes? Well, this is always a little bit annoying. In principle, so this is you can think of this as a charge. So in principle, you can have negative charge, and you would interpret that as anti-brane. So you can definitely have a branes and anti-branes. Of course, the number of branes is always positive. I mean, if you want to interpret the number of branes, that's always positive. But on the D brane, there is a relation between mass and charge, especially in the supersymmetric case. So once you fix, especially if you have supersymmetry, where you fix some conventions, then these signs have to be fixed somehow. However, there is always at some point when you get bogged down in fixing the sign, because you could define a different notation. So I'm not going to resolve this confusion completely, because it depends on your what I'm saying is that the number of branes, by definition, is a positive number. So if you want to interpret as a number of branes, then this has to be positive. If you think in terms of charge, this can also be negative, which is fine if you have only one brane. But as soon as you have more branes, for example, just 2 parallel branes, then they have all to be of the same charge, because otherwise it would not be supersymmetric. So you can't have brane and anti-brane. That gives rise to other issues, that they're not stable, they annihilate, and all of that stuff. in general, if you have more fluxes and more cycles in your solution, these quantization conditions are such that this number is an integer without a sign. So it can have also negative sign. So the quantization condition itself does not fix the sign. That's what I'm saying. It's the physical interpretation that we are touching here that forces us to pick n positive in this case. Okay, let's not continue on that. Okay, so here n will be definitely a positive number. In fact, it will be soon enough an infinite number. How are we doing with time? I want to make a break, but let me see if this is a good point. Yes, it's a good point since we had a natural break. So let's take 5 minutes break. Okay, let's continue. So after having found the solution for a generic p-brane, let me make some remarks about this solution. So remark number one, these are supersymmetric solutions. So they solve the Killing-Spinor equation of the corresponding type 2b or type 2a supergravity. And again, it's a quite simple exercise. So if you are interested in understanding these supersymmetry equations, it's a standard exercise that I recommend to all my students to check the supersymmetry conditions of a particular brane. So you can pick that one that you prefer, the D2, the D3, the D4, and check that it preserves supersymmetry. Something that you will notice if you start doing this exercise is that because there are extra fermions from the gravitino, there is also the dilatino, there is an additional condition. There is not only the gravitino variation to put to 0, but also the dilatino condition to put to 0. And that does not contain the derivative of the spinor, and for that reason it's often referred to as algebraic condition. I decided to focus on these supersymmetric solutions, but there are also non-supersymmetric versions. Actually, they preserve 16 of the 32 supersymmetries. So they are 1/2 supersymmetric, all the D-brane solutions. There are also non-supersymmetric versions, and they involve some modification, some slight minor modification of the ansatz, where you introduce an additional function. Again, you can find these in many references, and they are often referred to as black brane, black p-brane. So for any of these solutions, there is another version which breaks supersymmetry, and as hopefully I will have time to discuss a little bit at the end of next week, there is an associated temperature, so there are finite temperature versions like black holes. Right? So that's why I call black branes. the other thing which is interesting for us is that for general P, they are singular as r goes to 0. So r is a radial coordinate, so naturally it ranges between 0 and infinity, right? It's a radius, so it's a positive number, it's a positive coordinate. At infinity, because of this choice here of including the factor, this constant factor here, they approach Minkowski space. And r goes to 0, well, this factor goes to infinity, but just looking at this, it's a little bit naive. I mean, it's very naive. You really have to check the curvature of your solution, as you do in GR. You have to check that all the curvature invariants are well behaved, and so on. So the statement is that in general, they are singular as r goes to 0, if you do this check carefully, except for the very special case of p equal 3. So p equal 3 will be our favorite number from now on. So for p equal 3, I can use a different color for the chalk, and I can start simplifying things or specifying things, right? So the main thing I have to do is to set this to 1 for p equal 3. So green means p equal 3. And while of course here the ranges will be between 1 and 3, etc., etc. So the only other thing that I should do is that H3, let's write it, is going to be 1 plus L to the 4th, R to the 4th. Okay. R to the 4th, it will be quickly embedded in your neurons that it corresponds to the harmonic function in 6-dimensional transverse space of the D3 brane. And finally, the constant L, okay, I can use this space here. The constant L also takes a particular value. So L to the 4th, it's convenient to write in this way, is, after including all the factors and even the factor of dp here, 4 pi gs alpha prime square n, which I want to write also in a different way. So I will also write this in this way, which I want you to keep in mind. 2 pi to the 4th gs alpha prime square n. The most important feature is this n, but also these other factors will play a role soon. So here I will introduce the volume of the 5-sphere, which it's at this stage a seemingly stupid way to write pi cube, but at some point I will use the fact that instead of the 5-sphere here, I could have a different manifold, and then this will change this number here, and in fact all the rest of the considerations will just carry on. So L in the D3 brane is fixed by this number, and the Dilaton is constant, so that was meant to be a highlight of the solution. Okay, and moreover, it is not singular. So because it's not singular, it then makes sense to study the solution near to r equal to 0. And actually, if you do that in detail, we'll also discover another way to show that it is non-singular, because we will just write explicitly the behavior of the solution near to r equal to 0, and we will find that it is a perfectly fine, beautiful geometry. So we study the limit for p equal 3. R going to 0. I mean, not R strictly equal to 0, because it doesn't make much sense, but R approaching 0. So this limit is called, another word, buzzword that you probably have heard before, near horizon limit, but more accurately, I would say it's a near brain limit. Right? So in this picture, it means that we are focusing into this region here. Well, here, near to the brain. So in fact, by doing that, we are really starting the ADS-CFT part of the lectures, because this is the limit that Maldacena did in his original work to motivate the conjecture of ADS-CFT. So we will follow his steps, and we will precisely do the limit and interpret what this limit means in terms of physics, and that will lead us to quote his conjecture. I stress the fact that it is a conjecture, because from all these steps which I'm about to do, it does not follow that ADS-CFT is true, but it's a way to motivate. It's not a proof. So we will follow Maldasena's original reasoning, and we will consider the following thing. So we will consider alpha prime into 0 with R over alpha prime held fixed. And this is an energy scale, okay? Because this has the dimension of length square. So we define this quantity U. All of this is following closely Maldasena's original paper, which is the best reference than any other book. So the 10-dimensional Newton constant, G10, which is equal to 2 to the third pi to the sixth alpha prime to the fourth GS squared, also goes to 0. So at this stage, I'm also holding GS fixed. So this is the first limit that I'm doing. And so because this Newton constant goes to 0, then the brain theory decouples from the bulk. So the theory on the word volume of the brain, which I'll mention later, decouples from the bulk. So this is known as the coupling limit also, as another way to discuss it. So in particular, alpha prime corrections, in addition, to the supergravity action, are suppressed. Okay, so after these preliminary comments, we can actually implement the limit mathematically just at the level of the solution there. And just the technical device is to change coordinates, go from R to U, and then do the limit So H3, which I'm going to just call it H, becomes 4 pi gs n divided u to the 4th alpha prime squared in this limit. So the factor of 1 is clearly subleading to this factor that goes to infinity. So here u now it's a coordinate which is held fixed, but alpha prime goes to 0. So this factor is much bigger than this one. So we drop this 1. And then it is just a matter of plugging in this expression for the harmonic function into the full solution and finding out what the solution is. So the full metric, maybe I will skip one step, becomes the following. Okay, I've skipped one simple step, and the simple step is to write this part of the metric in spherical coordinates. So you write that as dr squared plus r squared in a metric on a round phi sphere. And then after this change of coordinate here, you can take the r part, the GRR component of the metric, which becomes the GUU part of the metric, and put that together with the first part, which has 4 coordinates. So that together gives this factor here plus this factor here, and the metric on the phi sphere, if you follow the scaling, we'll see that it becomes multiplied just by constant, right? So it's a very easy thing to see, but roughly you can see, because you have the r squared, well, yeah, you have a r squared metric on the 5 sphere, and then this is multiplied by h to the 1/2, but h to the 1/2 goes like 1 over r squared from here, so then this becomes r squared, and then up to some constant, which is this constant here, you get this expression. Yes? Yeah, it's another way to write the flat Minkowski metric. Yeah? It's that line above there with p equal to 3. Exactly, yes, thanks, yes. So the interpretation is that the number of branes is n. I forgot to, when I draw the picture, instead of drawing the canonical picture with many branes, I drew the one with 1 brane. But that's the canonical picture, right? So I wrote them in this way, but actually they're all on top of each other. You can also, in fact, take them apart. It's relatively simple to do that at the level of the supergravity theory by replacing this function here with a multi-center function where each brane will have its own position. And then you have other constants that parameterize the distances between the brane. So here we are in a situation where they're all coincident, so that's why you get this simple function. And of course, if n was equal to 1, that would be the solution for one brane. But for the moment, we keep n generic, and then in a few seconds, we will see that this n has to be large. But anyway, before doing any further limits, we can recognize something very nice. So this metric here, I already told you that contains a factor of S5. And if you go back to the notes from last time, you should recognize that this 5-dimensional metric, it's one of the presentations of ADS5 in one of the various coordinates that I presented. So the output of this limit is that near to the brane, the full space-time geometry looks like ADS5 cross S5, where L is now the radius, and not casually, I use the same notation as I used last time. L is the radius of ADS5, and also of S5. Okay, so the phi sphere has a radius given by L, and ADS5 has also its own radius parameter given by the same L. So there is only one single parameter, and the two radii are tuned in a way that they're correlated. And this correlation actually is related to the fact that the solution preserves supersymmetry. So you should not be surprised that it preserves supersymmetry, because the D3 brane solution preserves 16 of the 32 supercharges, and this limit, it's a non-singular limit, so it really should not do anything bad. But in fact, it does the opposite. It enhances the supersymmetries. So that was not forbidden by any kind of reasoning. And in fact, it helps, it arises, and it has also physical interpretation when we come to the ADS-CFT itself. So it preserves the maximal number of supersymmetries, exactly as the counterpart in 11 dimensions, ADS4 and ADS7. So the scale of the full solution, scale of space-time, the dimensional full scale of space-time, is set by the unique parameter L, which is correlated to n through this flux quantization condition. So we can tune L. You can take small, large, or whatever, by tuning appropriately all the factors of alpha prime, GS, and etc. So the curvature, in particular, for example, the scalar curvature or some higher power of the Riemann tensor and so on, are set by the parameter L. So if you compute the Ricci scalar, it will depend on L, etc. And if we want small curvature, we see that we have to take the following dimensionless parameter to be large. Which, if you follow through the previous discussion, means that GS n has to be also large. Okay. So in order to trust the supergravity approximation, this is in a sense equivalent to the limit that we have already taken, that alpha prime goes to 0. We have to take this limit here. Moreover, so in addition, on top of this, to suppress string loop corrections, let me say a few words now on these corrections. We have to take, so we have n very large. So in this inequality here, GS is held fixed for the moment, and n has to be therefore large. Now I'm talking about two different types of corrections. I mentioned alpha prime corrections and also string loop corrections. Now, of course, I have not done theory, and you probably will. Yeah. Yeah, I may have written it in a inappropriate way. Oh no, sorry, it's just that it was here. Yes. So I'm taking here the string theory perspective because I really want to formulate my ADS CFT correspondence in the context of string theory, but I'm starting from supergravity. Okay, so I have to view, or I want to view supergravity as the low energy approximation of string theory, and as I said, you can get the supergravity action of type 2b, for example, as this approximation, but you will have also corrections. So if you keep computing corrections in a perturbative expansion, you will have two types of corrections. You will have corrections in alpha prime. These are 3 levels in string theory. So these are higher order in the curvature. Right? So no one told us that there is only the term R for the kinetic term of the metric. There will be also higher derivative terms. But these will be accompanied by higher power of alpha prime. So in this limit of alpha prime going to 0, they are suppressed. But there are also corrections from string loops. And they will be suppressed, so we don't have to worry about them if we are taking this limit of large n. So at this point, for us, GS has been defined as the string coupling given by the expectation value of the dilaton, and n is just the number of branes, some positive number. So we would like to reinterpret this limit later in the light of the ADS CFT correspondence. And so before doing that, as a last topic for today, I would like briefly to remind ourselves what is the other description of the brane in terms of open strings. And for us, it will be important to use the low energy description of the open strings, which is that in terms of gauge theory, Young-Mills theory, so that we will have set the stage. We'll have described the branes from two different points of view. One point of view as the gravitational solution, which I can consider in this particular limit, where supergravity can be trusted in addition. And also, I would like to see what is the implication from the open string point of view. And that will give us the, we'll set the stage for formulating the ADS CFT correspondence, which I think I will do, strictly speaking, on Monday. So, but let's start by making this small intermezzo with the D-brane as super Young-Mills theory. Okay, so the brane, as I just mentioned, can be viewed as Sugra solutions, and this comes from the closed string point of view. Of course, the type 2 strings are closed strings. Or as extended object strings attached. And the strings attached are then clearly, by definition, open strings. Okay, so we discussed that part already, basically in the past hour or so. So I would like to spend a few minutes now a little bit on this open string point of view. So the picture, coming back to the picture, is that you have the multiple branes that later we will take to be coincident, but just for the purpose of writing a picture, we take them to be separated. And then the open string can attach on one brane and end on the same brane, or can attach on one brane and end on a different brane. Right? So you have all these possible modes that are on the n dp branes. And really here we assume that the space is just flat space. Now, the low energy effective description of this and I hope that Rodolfo will discuss this a bit. On n coincident d branes, so now we really put the branes together, is for dp brane, p plus 1, sorry, I was just confused about the dimension. So p plus 1 dimensional super Yang-Mills theory with gauge group UN. Okay, so that's the statement. And the way to understand that without doing any detailed computation is to start, for example, from 10-dimensional Yang-Mills, and reduce that to p plus 1 dimensions. Or alternatively, to think of the various modes that arise on the word volume of the brain and transverse to the brain. So the modes that describe motion on the brain and motion in the normal direction to the brain. So in this way, we can realize that the fields of this theory are, well, of course, a non-abelian gauge field, A, that propagates on the word volume, and the fields are supposed to be described by these branes, where they have two Chant pattern factors, which are the indices ij of a adjoint representation of UN. And the transverse directions, on the other hand, are given by scalars. So from the Lorentz group of the p plus 1 dimensional Minkowski space, these are scalars. They are 9 minus p scalars. But since there is only one gauge group, UN, and as I said, you can also think in terms of using from 10-dimensional Yang-Mills theory with gauge group UN, these scalars are transformed in the adjoint representation. So I cannot choose any representation which I want. You would think that, okay, then the ADS-CFT is a bit boring because I am stuck with these particular theories, which are very special. But in fact, it's possible to manufacture more complicated theories with matter in many different kind of representations, with gauge groups which are different from UN, etc., etc. But of course, this requires more advanced material and tools. So this is just the basic setup. We start with the flat branes embedded in flat Minkowski space. There is no any fancy Calabi-Yau or other manifolds around. So that's all that you get in that simple situation. And then the fermions are Gauginos, of course, also transforming in the joint representation as everything. Now, once we are happy and we believe that this is the field content that arises from the low energy modes of the string, then we can cheat, as it were, in deriving the action, because that will be fixed by supersymmetry. These theories are highly supersymmetric, so supersymmetry essentially fixes uniquely the form of the action. So if we want to write down the action, the only thing that we can get is the action for the corresponding supersymmetric Young-Mills in the given dimension. So we can say that somehow supersymmetry fixes, which is very high, fixes the form of the action. And the action will be, will be the standard action, the standard form with a kinetic term for the non-abelian gauge field and a kinetic term for the scalars, with some particular potential interaction, which again is fixed by supersymmetry. And the simplest way to derive it is from reducing the pure Young-Mills theory in 10 dimensions and then getting this down, where the transverse component of the abelian gauge field, of the non-abelian gauge field in 10 dimensions will then give rise to the 9 minus p scalars, as much as in the Kaluza-Klein reduction, which I've done for 11-dimensional supergravity down to 10-dimensional supergravity. There is an alternative point of view on this, on how you get Young-Mills theory on the brain, which goes through the effective description as a collective coordinate modes for the brain, which is that in terms of Born infield action. So this is best understood, unfortunately, for just the case of n equal 1, but then somehow one can extrapolate to some extent to the case of non-abelian. So n minus 1 dp brane, sorry, n equal 1 dp brane has an effective action that captures the interactions up to, including higher order corrections in alpha prime, which is given by this expression similar to the Nambu-Goto action for the string. Namely, it contains a determinant in the following way. So it has a coupling constant, which is the tension of the brane, and it has a p plus 1 dimensional word volume, couples to the dilaton, because we learned that all the branes couple to the dilaton, and then it has this square root of this determinant of, here I write the metric as a matrix, as a symmetric matrix, and then in this same notation I write the word volume gauge field that arises from the quantization of the open string modes as an antisymmetric matrix. So I can sum G to F. So here I'm taking a symmetric matrix and summing an antisymmetric matrix. So the total will be a matrix with p plus 1 times p plus 1 entries and I'm taking the determinant of this matrix. Now, TP, the tension of the brane, can also be derived from some string theory computations, and is given by 2 pi p alpha prime p plus 1 gs. Again, in the convention where I put gs explicitly in front of the constant part of the dilaton in front of the action. Okay, so if we believe that, and I don't know if Rodolfo will discuss it or not, we can then take, as a simple, very simple exercise, we can take the alpha prime going to 0 limit, which is the limit that you are interested in. See what we get. So we take alpha prime to 0 in that action there, with holding fixed gs times alpha prime p minus 3 over 2. I'm keeping p generic. Main interest is p equal 3, then this alpha prime actually drops out from this expression here. So main interest is in p equal 3. But you can carry out this computation for any p. And from that limit, then you get an expression for S, which has an expansion in alpha prime, right? So you just take the determinant and expand this in powers of alpha prime, just in Taylor series. And then you get a leading order term, which will look like dp plus 1 over volume e to the minus phi, just from there. And then the first non-term is an f squared. So you exactly reproduce the kinetic term. If you had one brane, that would be the Maxwell kinetic term. And then if you could do that for n branes, that would be the Young-Mills interaction. So then, in keeping with this notation, here we get the factor, which is the Young-Mills coupling, so the gauge coupling of Young-Mills. So this is by definition what you get when you do when you get this in front of this action. So this is by definition G Young-Mills. And then by comparing this G Young-Mills with the tension of the brane, I can obtain a relation between G string, alpha prime, etc., with G Young-Mills. And the relation turns out to be the following: G square Young-Mills is equal to GS 2 pi p minus 2 alpha prime p minus 3 divided by 2. So in particular, there is no alpha prime for p equal 3, and we see that up to some factors, 2 pi, etc., G Young-Mills square is nothing but GS. Yes? Sorry? By definition, I'm keeping the dilaton inside, okay, and I'm putting in front of the action the constant part of the dilaton. So if we are in generic P, you will still get this dilaton, which is a bit annoying. But for P equal 3, the dilaton is constant. So because I put this already out, then for P equal 3, this is equal to 1. Right? So the constant part is already pulled out. Okay, so then here we get our other favorite relation, that is that we will implement when we are going to formulate. So here I'm kind of accumulating information, right? So here I get this relation, and the relation is that G string is with some conventional factor of 2 is equal to G Young-Mills square. So you see, I'm building up a dictionary because I'm relating the coupling constant on Young-Mills to the G string, and I have related already by construction the n, so the dimension of the gauge group, UN, to the number of branes. So that will be essentially all I need in order to then describe the limit, which I've done in the near horizon, also at the level of the Young-Mills theory. So going back to p equal 3 now, this description here then condenses into what is known as n equal 4 super Young-Mills theory. Okay, so again, by using my method of putting different colors, if you are in p equal 3, then we have a non-abelian gauge field in 1 plus 3 dimensions with gauge group UN, and then we have 6 scalars in the adjoint of UN, which are exactly the transverse direction to the D3 brane. And they all repackage into an action which has the maximal amount of supersymmetry in the given dimension, which is 4. And the maximal amount of supersymmetry in 4 dimensions is n equal 4. So this n equal 4 is a reformulation of the fact that the theory preserves 1/2 supersymmetry. The D brane that we started with. I am not going to write explicitly the Lagrangian. I think you will see it in Ali's lectures. It contains, as I said, the kinetic term for the Young-Mills field, and the kinetic term for the bosons, the scalars, and the gauginous, and then some potential, which you can also rewrite in some superpotential in terms of the scalar and its supersymmetric completion. So anyway, all of that can be written down completely explicitly. There is no mystery, and it's just the Lagrangian, which actually can be written in one line. So I will not do that. Now, this Lagrangian, which I'm not writing, has manifest SU4 symmetry. So this SU4 has nothing to do with the gauge group. This is a global symmetry. Okay, where does it come from? If you remember that at the level of algebras, SU4 is equivalent to SO6. This SO6 comes, its origin is in the transverse symmetry to the brane. And you can see that the fields that appear in the theory actually arrange, almost by definition, because I'm telling you that this is a symmetry of the theory, arrange in representations of this symmetry in a way that the full Lagrangian is invariant. So let's see which representations they are. Perhaps the most obvious one is the fact that the scalars, which I will denote phi with an index I, transform into the 6 of SU4. Right? So the 6 is the vector representation of SU4, which is also the vector representation of SO6. So they transform as a vector with 6 entries. The fermions, which I will call lambda, and I will put an index A. So here I goes between 1 and 6. And the fermions actually turn out to be 4 So here I put a lambda. I should have put a if I want to keep to this with this notation, where a goes between 1 and 4, and not surprisingly, they transform as the vector, well, as the fundamental representation of SU4. And in fact, the supercharges that one could compute just from the basic fields of the theory, they also transform in the 4, okay? So at this level, this 4 is related to this 4 that appears here, okay? So there are 4 supercharges, and they transform as a 4 of SU4, and this SU4 symmetry that transforms the supercharges and acts also on the other fields. The gauge boson, by the way, the bosons do not transform under that. It's called an R symmetry. So R symmetry is any global symmetry that acts upon the supercharges of a supersymmetric theory. That can be a global theory or also supergravity, as we've seen last time when I explained gauge supergravity as a gauging of the SO2 equal to U1 R symmetry. Okay, so the manifest symmetry of this theory of Super-Yang-Mills with n equal 4 in 4 dimensions, what is it? So can someone suggest me what is the manifest symmetry of this theory? Even part of it. That makes the question easier. I am disappointed. Can you say SU4 at least? The question is, what is the symmetry which is manifest so far of this theory? My previous statement was this theory has manifest SU4 symmetry. Okay, so this was an easy question. But in fact, the question was meant to make you think that the full manifest symmetry is that of Poincaré group times SU4. Or by changing the notation in front of you, Poincaré times SO6. Right? So that's the symmetry, the manifest symmetry that this theory and its Lagrangian, which I have not written, has. Can I take 5 minutes or something like that?
Yeah, so we will have to begin the next lecture at 11:30 sharp, because then we have lunch. Maybe 5 minutes, not really.
Yeah, 5 minutes, maybe less than that. Yeah, it's just half a page. I would like to finish this discussion. So, and this happens for all P. In the Super-Yang-Mills that you derive from the brain, you always have Poincaré in P plus 1 times SO P minus 9 minus P, whatever. I mean, that number is the transverse directions. Yes, 9 minus P. So the generators are P mu, J mu nu, which are, so there are 4 of them, 6 of them here. But n equal 4 is a special, and it is actually a conformal theory. So it has additional symmetries, which are the dilatation, that's one other generator, and the special conformal transformations, which are additional 4 generators. And altogether, this, if you add them up, right, you will find that, so special in the sense that it is a conformal theory. altogether there are 15 generators, and if you actually compute the commutation relations, which is not something which I can do in 5 minutes, or maybe not even in half an hour, but if you do that, you will find that they will rearrange into the commutation relation of the group SO2,4, of which the Poincare group is a subgroup given by the 10 generators of Lorentz plus translations, but given the additional transformation that do not commute with the rest, they form an algebra, and this algebra is SO2,4. And of course, this algebra, I already mentioned that in words, is the conformal group in D equal 1 plus 3 dimensions. Okay, so now I can ask a slightly less trivial question to my previous one, and what is the symmetry, which is not so manifest? The full symmetry of this theory is then not just Poincare times SO6, but it is full symmetry is SO2,4 times SO6. And in fact, this is the bosonic part of a supergroup, right? And the supercharges also are part of the generators. So when you compute the supergroup, you get also some fermionic part, which is parameterized by the supercharges. So the supergroup has a name, which now I should check what is exactly the name. It's something with the bar inside, which at the moment I don't remember. But it has, as promised, it has a full, so maximal supersymmetry. So it has 32 independent components. Right. Okay, so let me stop here because I'm really late. And from next time we can start really by recapping quickly what we said today and stating the ADS-CFT conjecture.